So today I would like to present work in collaboration with Morten Kringelbach and Gustavo Deco. And the title is Less is More, but really the importance here is on the importance of long-range connectivity in, or long-range exceptions in brain architecture. So if I were to ask you, what is the shape of water? Perhaps you would think about it for a while, and then perhaps you would say that it might be the container that shapes the water. And indeed, as in the case of a river, the river is, or the water that flows in the river is determined by the riverbed. And this neat fundamental phenomenon that we observe across nature can be summarized by this line that says that the content is determined by its container. And really, indeed, this is what we're trying to do when, in this session, we're trying to link structural constraints and understand how they give rise to the brain activity, the brain functionality. And so if we go from structure to function, we are looking for features of anatomical or structural features that will sort of explain this, this link. And for the purpose of our argument I'm trying to make here today, I will focus on the two perhaps fundamental constraints that we've been interested in, namely the geometry of the brain, which describes the cortical foldings in the brain, and the anatomical connectivity, which is more concerning with the white matter axonal bundles that connect distant brain parts of the brain. And recently, there's been work showing that indeed geometry might represent a more fundamental constraint on the dynamics than the white matter connectivity and this interregional connectivity. And in this paper by Punk and colleagues, they, by using neural field theories, they decomposed fMRI activity, or decomposed the structural, the geometry of the brain into fundamental modes, and reconstructed fMRI activity in the spontaneous and task-evoked in these two data sets, showing that indeed geometry, as far as the reconstruction is concerned, with 200 modes, performs better than the connectome or the white matter connectivity. What I would like to argue here, or at least give some glimpse, is that perhaps geometry and connectivity can be thought of as two sides of the same coin, and perhaps it might not make sense to think of them as a dichotomy. And I guess the key here is the idea of the exponential distance rule, which has been proposed by Henry Kennedy and colleagues, that essentially says that the anatomical architecture of the mammalian cortex uses similar short-range wiring with an exponential drop-off in strength over distance. And this is commonly known as the exponential distance rule. So in simple terms, what it says is that if you have a short Euclidean distance, then this model would predict that the connectivity in the brain is going to have a higher weight, connectivity weight. Whereas if you have a long Euclidean long distance between two parts of the brain, this model would predict a weak weight. And this decrease is defined by this exponential drop-off. And so with this, we can define a new or a different structural constraint that might be used to give rise to the function that we observe in fMRI. And here really what we're doing is that we're using the information of the white matter connectivity, and we fit this exponential distance rule to define the exponent with the information of the geometry. So in some ways, these are intimately linked. The second point of the argument is that, but perhaps this is not enough. So yes, what white matter connectivity gives rise or is related to geometry, and geometry is related to this short range connectivity. But really what matters is this long range exceptions. Perhaps anecdotally, Henry Kennedy has said that he's not interested in the EDR itself, but mainly these exceptions to the rule. And what are these? Well, in their work in the macaque monkey with a painstaking track tracing study, they've shown that the macaque brain contains a subset of small long-range exceptions to this exponential distance rule. And again, what it means is that if I were to plot the fiber density, this is done in a diffusion tractography on the humans, but the idea sort of is the same, is that if we have a fiber density plotted over the distance between different parts of the brain, we can fit the exponential distance rule here in the, I guess you can see that, yeah, in the red, and then we can look at connections that have stronger weights that would have been otherwise predicted by the EDR alone, which are the ones in red. And in a recent work, whole brain modeling work, it's been shown that by Deco et al. That if these long-range connections are added to the exponential distance rule network, they improve reconstruction of long-range functional connections, which are usually underrepresented in whole brain models, or improve different information processing quantities such as information cascade or susceptibility of the network. So just to recap, I guess here I'm claiming is that perhaps short-range connectivity and geometry can be thought of as two sides of the same coin, and they are intimately connected through this EDR. And maybe what really matters is this long-range connectivity, which is important for critical information processing of the brain. And so we tested this, so in a similar way to Pang et al., the work on geometrical modes by using the spontaneous fMRI activity and task-evoked activity, and by using the Euclidean distance and the white matter tracts, we derive, we use the traditional geometrical representation, two different representation of this EDR rule, but I will just talk to them. I will talk about them in general for the sake of this argument, and then we've created this new graph representation that connects this exponential distance rule short-range connectivity with these long-range exceptions. And just to kind of intuit what we're really trying to do here is that we're sort of changing the topology by adding these long-range exceptions that sort of can be thought of as some spatial wormholes or spatial shortcuts that connect different brain regions that would not have been otherwise predicted by a spatial relationship as predicted by the EDR or geometry alone. And so we took these graph representations and we decomposed them into the fundamental harmonic modes. Here I'm showing you the decomposition for all the 4 different graph representations. You heard in the first talk that we end up with these standing wave-like patterns, which can be thought of as a spatial extension to the Fourier decomposition in a signal terms. So we end up with these spatial modes that vary in spatial frequency. And then we were interested in looking at these functional features that might be important for this optimal information processing in the brain. So we look at the reconstruction accuracy of the long-range exceptions of the spontaneous functional MRI. And here, as done before, we show it for the first 200 modes. And as I'm showing here on the right, you can see that the EDR plus long range seems to accurately represent these connections in comparison to the EDR alone or the geometry. Moving on to the task evoke data, we also reconstructed the activation maps from the HCP canonical 7 tasks at first. Shown here on in the A panel, and we did it for the 200 modes. But what have become obvious is that really at the elbow is where we get the most increase by adding the different harmonics. So what it essentially means is that if you take the n number of modes and 1 plus number of modes and take the difference, we can see what modes are adding the most information in reconstructing these activation maps of the HCP tasks. So, and as you can see here, it's about 20 modes. So we focus on these 20 modes. Maybe a bit further. So we focus on these 20 modes and reconstructed the activation maps for all the 47 HCP tasks, and then compare them between themselves. For the purpose of this talk, again, we can here focus on the geometry and the EDR plus long range, and where you can see in blue where the EDR plus long range reconstructs more accurately the results, whereas in red you see the opposite. And here at the bottom, just showing the average across the task, showing that the EDR plus long range can reconstruct the data well. And again, it's probably might be no surprise, because really what we're adding these long range connections, which sort of are enabling us to fast forward or shortcut different spatially distant regions, which should be important for complex cognitive tasks such as these 47 HCP tasks. So just to sort of kind of wrap up, then we can think of these activation maps and the fact that they can be reconstructed through a couple of fundamental modes rather, that sort of describe most of the activity that we see in the brain, and so, but these inherently have this long-range connectivity, these long-range exceptions embedded in them, and therefore enabling to accurately reconstruct these cognitive tasks. And so in conclusion, the way we think about this structural constraints, that perhaps short-range connectivity and geometry are two sides of the same coin, that the long-range connectivity exceptions are what matters and are instrumental for brain function. And when we use this intuition of the short-range connectivity plus these long-range connections, we can reconstruct accurately spontaneous fMRI as well as task-evoked fMRI using a subset of few brain modes. And yes, please, if you want to discuss, I'll be at the poster 1826 tomorrow and on Thursday. And there is also preprint of this work if you want more methodological details. Thank you very much.
We will end this RS session with one last question. So a question is, are these long-range connections involved in like a certain large-scale functional brain networks?
Yes, so you mean the harmonic modes. So we have not looked at, that was not part of this study, but in line with what has been done previously by Atasoy et al., it is possible to link them to functional networks. And there is a tendency that in these, because they're spatially varying, so the lower frequencies will have a more global modes, and these would, some of them would relate to some of the resting state networks, for example.
Okay. Thank you everyone for attending the session.